To watch more videos like this, subscribe. Click on the bell to turn on notifications. Click on the like button. Share.
Hello friends, now we will start with the next chapter of analog electronics, that is the power amplifiers. This topic is very important from examination point of view. You have lot of questions in engineering services and in different PSUs from this chapter. So we will be covering all important points and all important topics of the chapter, but purely from examination point of view. Before I start with the topics of this chapter, so let us have a look at the whole syllabus which is likely to be covered in the chapter. So first I will be giving you the small introduction to the power amplifiers. Then we will be talking about the classification of power amplifiers. That is the next topic. Then we will be talking about the distortion. Distortion is important parameter of power amplifiers because these amplifiers introduce a distortion in the signal at the output. So distortion is one of the important topic which becomes important for the chapter on power amplifiers. Then we'll be talking about the class A amplifier. Class A amplifier is important. You have questions from this topic. Then in class A amplifier we'll be talking about the three different types of class A amplifier, that is class A amplifier with direct coupled load, then class A amplifier with transformer coupled load, and then push-pull class A amplifier. These are the three different types of class A amplifier we are going to cover in this chapter. Then I'll be talking about class B amplifier, and in class B amplifier we have again two types of the amplifiers, that is transformer coupled class B push-pull amplifier and class B amplifier with complementary push-pull arrangement. We will see these amplifiers one by one, and then I'll be talking about class AB operation, that is class AB amplifier, and lastly we will talk about the class C amplifier. There is one more amplifier, that is class D amplifier, which is not discussed separately, but I'll be discussing that amplifier in classification of power amplifiers. So this is the whole syllabus from this chapter which we are going to cover one by one. And remember, this chapter is important purely from objective type point of view. You have many questions in objective type papers from this chapter. So let us start with the first topic of the chapter, that is introduction to the power amplifiers. The power amplifiers are basically the large signal amplifiers. What do you mean by large signal amplifiers? The signals which are having a high power level. If you talk about a simple amplifier, normally voltage is in the range of maybe 5 volt, maybe 12 volt. Current is in the range of milliamperes. When the power level of the signal increases, for example, suppose you are giving some speech publicly, so what do we need? We need to have a microphone. We need to have certain amplification stages, and then finally I have a loudspeaker. So your voice is amplified and you are able to reach to the crowd through the loudspeaker. So the amplifier just before the speaker is known as power amplifier. So that is why what I said, these are essentially the large signal amplifiers which amplify the large signals and normally connected at just before the output stage, and that output stage could be a speaker or it could be a transmitter in the communication system. So amplifier just before the transmitter. Why? Because I need to enhance the power level of the signal before transmitting in the air. So before transmitter as well, we have an amplifier which is known as power amplifier. So let's have a small look. So these are essentially what? Large signal amplifiers, which enhances the power level of the signal at output stages. These are used what? At the output stages to deliver power to the load, such as what? Speaker at audio frequencies and signal transmitters at radio frequencies in communication systems. And remember, when you have large power, large signals, then the small signal model of the BJT is not applicable. The small signal model cannot be used for analysis of these amplifiers. Why? Because of the distortion introduced by non-linearities in the characteristics of BJT. What is the meaning of that? Just try to understand. If you remember the characteristic of BJT, these are the two axes where the y-axis is collector current and x-axis is nothing but voltage VCE, right? And if you draw the characteristics are like this. I have a line which is almost parallel to the voltage axis VCE. These are the characteristics of a BJT. So now suppose, and what is this? This is basically every characteristic represent a base current, maybe IB1, IB2, I have IB3, then I have IB4, right? Now suppose this current is 1 microampere, this current is 2 microampere, this current is 3 microampere, this current is 4 microampere. So what I find, the base current is changing equally, 1 to 2, 2 to 3, 3 to 1. So change in base current is 1 microampere. But if you see in output characteristics, your collector current is not changing equally, it is changing unequally. That is nothing but non-linear relationship between the collector current and base current. And if you remember, mathematically collector current is function of base current, and this is what we take normally. The collector current is equal to beta into IB. That means if beta is a constant, which is gain of the BJT, so IC is proportional to IB. Mathematically that is not correct. This is practical. Here IC is proportional to IB, but here IC is not proportional to IB. Why? Because this is ideal condition which is considered. Otherwise IC is function of some constant, say alpha plus beta IB square IB plus gamma IB, that is IB square, and so on. Basically it is not directly related to the base current, rather it is related to the powers of the base current. So that is nothing but non-linear relationship between collector current and base current. This is what you have. And in that case, if my collector current is not proportional to base current, so if base current is sinusoidal, the collector current will not be purely sinusoidal, it will be having harmonics. It will be having multiple frequencies, which are the multiple of the frequency of the base current. So whenever there is no linear relationship between base current and collector current, even though base current will be having a single frequency, the collector current will have multiple frequencies, and these frequencies introduce a distortion in the output signal, which is nothing but non-linear distortion. So the large signal amplifiers are basically having that problem of non-linearities in the characteristics of BJT. Fine. So this becomes important from that angle. There is always some distortion when your signals are large. Fine. So now please see what I told. There is harmonic distortion introduced in the output even if base current is sinusoidal. So harmonic distortion is important quality parameter of the power amplifiers. Fine. And then there is another important parameter, that is power conversion efficiency. Power amplifiers are essentially used to enhance the power level of the signal. So power conversion efficiency is another important parameter of power amplifiers, which is required for prolonged battery, high temperature stability, and so on. These are few points, of course, not necessarily from examination point of view, but important from the relevance of the topic for different competitive exams. Fine. So this is all about introduction. But before I proceed with further topics, I will be having very important topic, that is nothing but operating point and load line revisited. What is the meaning of that? Let us see, let us understand. This is a basic BJT circuit. I have the base resistance, I have the collector resistance, which is nothing but a load. I will be considering, I am connecting a load in the collector circuit. Output I am taking from the collector. When you draw the characteristic of this BJT, first let us talk about the characteristic of BJT. These lines, I have x-axis which is nothing but voltage VCE, I have y-axis which is nothing but what? The collector current, and these lines, please see, these lines are nothing but representing the characteristics, and every line is for a particular base current. Fine. So these lines are nothing but characteristics of BJT. Now, if you write expression of voltage VCE or V naught here, what is voltage VCE? Voltage VCE here is nothing but voltage VCC, that is voltage VCC, minus what is there? I have the current IC, suppose. So current IC, I'm taking small letters, so that is IC into RC. So what will be current IC here? Current IC will be equal to what? That is nothing but minus 1 by RC into VCE, right? And plus, that is VCC, upon RC. This is what you have. Mathematically, IC is function of VC, but that is coming from this circuit, not BJT, right? For characteristics for BJT is nothing but these lines. Now, if you write mathematical expression of current IC in terms of voltage VCE, this equation is known as load line. Even though I have discussed this in detail in my different topics on BJT amplifiers, but you should be remembering this equation represents what? A load line. Fine. So if you draw this line, so when voltage VCE is 0, what is IC? That is VCC upon RC. So when voltage VCE is 0, this point represents VCC upon RC. And when voltage VCE is 0, so when current IC is 0, you can take this on the side, so VCC becomes equal to VC, or VCE become equal to VCC. And if you connect these 2 points, and that is nothing but load line. This line is coming from the circuit of the amplifier or circuit of the BJT. So this line is known as load line. Now, the intersection of load line with characteristic of BJT, this is characteristic of BJT. So intersection of load line with characteristic of BJT is known as operating point or Q point. That is known as operating point or Q point. Now, interesting point. I give some signal. This is nothing but what is this? This is my base current, right? I give some current, that is base current, and base current is normally in microamperes. So suppose my base current is varying between these two ranges, right? So suppose my base current is varying from this IB1 to IB3 with IBQ as the center value, right? So this is the variation of base current like this, right? Sinusoidal. There is, suppose base current is sinusoidal, right? Input signal will be giving me the value of the base current, but this base current will be having two components. What are those components? One component coming from this side, that is input current, and another component will be coming from this side, that is DC current, right? So by this current will be having input current plus some DC current coming from DC voltage, right? So that is why if you draw this is DC current, DC value of the base current, right? And that is this current, that is DC current, right? So my total current in coming to the base will be having some DC value plus some time varying value, that is sinusoidal value. So it is varying around this value, that is DC value. So this is how I am drawing. So current is increasing. I'm sorry, I'll redraw that. So my current, base current will be varying like this. So some IBQ, that is this value, and it is varying around that IBQ, right? Like this. Base current is increasing, then coming to IBQ and going up like this, right? The corresponding variations in voltage VCE and current IC will be seen like this. When base current is increasing, this is increasing value of the base current. When base current is increasing, what is happening? My voltage VC is decreasing. Voltage VCE is decreasing, and when base current is decreasing, voltage VC is increasing. That is variation in the voltage VCE. And if you see the corresponding variation in collector current, you will have variation in collector current like this. So interesting point here is, when operating point lies at the mid of the load line, for sinusoidal base current, the collector current is sinusoidal and my voltage VC is also sinusoidal, right? But we will see another case. What is that another case? Let us see that. Suppose now the operating point is located here instead of here. So my base current may be varying from 0 to this, and it will be, although it will be sinusoidal, but varying about this value IBQ. It will be varying like this. Base current here will be varying around IBQ, right? But see this, my voltage VC will be sinusoidal here, but after this it will become 0 like this. Not V0, VCC. So it will be sinusoidal, but on upper side it will be limited to voltage VCC, because your Q point, your voltage VCC cannot increase beyond VCC, because that is the maximum possible value of voltage VCE. Now come to this side. If you see here, my collector current, when base current is increasing, collector current will increase here like this, but on downside my current cannot fall below this value, so it will not be sinusoidal. So what has happened? When my Q point is shifting towards this region, which is known as cutoff region of the characteristic of BJT, my voltage VC and current IC are not sinusoidal, right? And why? Because when base current falls below certain value, IB0, in that case your characteristics are not linear and your output is distorted. And this is what happens in case of power amplifiers. If input signal, I'm talking about input signal, base signal. If input signal is large and operating point is located near the cutoff, in that case, output signal will be sinusoidal only for maybe 1/2 of the cycle of input, right? So that puts constraint in the level of the signals which are to be amplified, and that is nothing but that is dealt in power amplifiers. So we will see all the amplifiers one by one, and we will see how to tackle these type of problems in power amplifiers. So this is all about the introduction to the power amplifiers and basic concept of the load line, which is essentially understood for understanding of power amplifiers. So I'll start with the next topic in next class, that is classification of power amplifiers. Thank you very much for watching the video.